Yes, so good day everyone, and I trust we are all doing great. We are all doing fine. So, in today's video, we are welcome to K-Sec Tutorials, and this is Mr. Kingdom. Um, so in today's tutorial video, we'll be looking at Gay-Lussac's law of combining volume. Gay-Lussac's law of combining volume is one aspect of chemistry you have to know um, if you are writing UTME, you are writing WAEC. Questions almost always come out. You are writing NECO. This topic is very, very important. And I can assure you that if you follow me through to the end, you are not going to be having any problem solving any questions on Gay-Lussac's law of combining volume. Ensure that you are following me to the end. You take notes and you follow me. Focus when you are listening to when you are watching this video. So get your biro and your pen ready. Let's delve into Gay-Lussac's law of combining volume. So let's go to the law. What exactly is Gay-Lussac's law of combining volume? So Gay-Lussac's law of combining volume. I hope my pen can work on this. Coming. Okay, yes. Let me give a brief introduction. It was actually discovered by someone called Joseph Gay-Lussac. I think Lewis Gay-Lussac. He was the one that discovered it in 1808. 1808. Now, Joseph Gay-Lussac was also the one that discovered what we call the pressure temperature law. He discovered what we call Gay-Lussac's law. I need to give this introduction so you guys understand properly what we are looking at. Gay-Lussac's law. So Gay-Lussac's law is different from Gay-Lussac's law. Gay-Lussac's law is different from Gay-Lussac's law of combining volume. Gay-Lussac's law is the pressure temperature law. It's part of it's one of the gas laws that we have. We have Boyle's law, we have Charles' law, we have the pressure temperature law, which is also called Gay-Lussac's law. So Gay-Lussac discovered Gay-Lussac's law and Gay-Lussac's law of combining volume. So Gay-Lussac's law is different from Gay-Lussac's law of combining volume. Gay-Lussac's law, let me just quickly state it. I did not write it here because that's not what we are looking at. It says that at constant volume, the pressure of a gas is directly proportional to its temperature. It means that as temperature increase, as you increase the temperature of a gas, its pressure also what? Increase. Is also is one of the gas laws that we have. You remember Boyle's law. Boyle's law states that constant temperature, the pressure of a gas is inversely proportional to its volume. So as volume increases, pressure decreases. As the volume of a gas increases, the pressure decreases. That's Boyle's law. And then there is also Charles' law that states that at constant pressure, the volume of a gas is directly proportional to its temperature. So this Boyle's law, Charles' law, and then there's what we call the Gay-Lussac's law, which is the pressure temperature law. This is different from Gay-Lussac's law of combining volume. So in case you are asked which of the following represent Gay-Lussac's law, is different from Gay-Lussac's law of combining volume. So this law here, where at constant temperature, at constant volume, the pressure of a gas is directly proportional to its temperature. As temperature increases, pressure increases. This is Gay-Lussac's law, not Gay-Lussac's law of combining volume. I hope this is clear. So let's delve into what we are looking at properly today. Let me clean my board. So Gay-Lussac's law of combining volume. Gay-Lussac's law of combining volume. Let's state it. Gay-Lussac's law of combining volume states that when gases react, they do so in simple whole number ratio. Take note, simple whole number ratio to one another and to the volume of the product if gaseous. provided the temperature and pressure remains constant. Calm down, I'm going to explain. Now, I wrote it here that the number in the simple whole number ratios mentioned in the law refers to the stoichiometric coefficient formed in a balanced chemical reaction. In the balanced chemical equation of the reaction, no? This should be balanced chemical reaction. Balanced chemical reaction. I'll just put it that way. So, now, there are things you need to take note of to understand this law very well. Let us repeat the law and we'll break it down. So, Gay-Lussac's law of combining volumes states that when gases react, that means Gay-Lussac was probably doing an experiment. He now discovered that during the reaction that involved gases, so we can use a gas as an example. Okay, let's use a reaction that involves gas. Which reaction can we use? Okay, let's use the reaction of ammonia. The reaction of nitrogen gas and hydrogen gas that formed ammonia, that forms ammonia. So N2 reacts with H2 to form NH3, right? This is the formation of ammonia. This equation is not balanced. Yes. So let's balance nitrogen. We have two atoms of nitrogen, two atoms of nitrogen here. We have 6 atoms of hydrogen here. This is just 2, so 3 here, 3 times 2. So we have 6 atoms of hydrogen here. So this is already balanced. 2 atoms of nitrogen, these 2 atoms of nitrogen. These 2 belongs to N and hydrogen. So 2 times 3 is 6 atoms of hydrogen. 6. So this is a balanced equation. So he now discovered that when gases react, in this kind of reaction, okay, they do so in simple whole number ratios, to one another, and to the volume of the product. And to the volume of the product, if this volume is gaseous, let's say we are doing an experiment and this volume is gaseous, is a gas, that means they also the way they relate to each other is that if this is a um if this is a gas also, all of them relate with each other in simple whole number ratio. Peradventure this is a liquid, we are going to neglect this. The reason I'm saying this is because there are times that the product may not be a gas. That means we take away the products, like the products in Gay-Lussac's law does not stand if it is not a gas. You must take note of that. It can be given sometimes. We are going to solve questions on it, like about, I think we have about 10 questions. We have about 10 questions. So, coming. Okay. Still recording. So, yeah. When gases react, they do so in simple whole number ratio. The way they react is in simple whole number ratio. Okay. So there must be numbers representing this. There must be number that we put in this ratio that represent the ratio, definitely. And I said it here, the number in the simple whole number ratio mentioned in the law refers to the stoichiometric coefficient. Stoichiometric coefficient is the number in front of the reactant and the product. If the product is gaseous, these reactants are gaseous too. So the number, remember, let me clean this. Remember that we have 3 here. So the way this relates to each other, this reaction, the way we can write it now is 1, because this stoichiometric coefficient of nitrogen gas here is 1, of hydrogen gas here is 3, and of ammonia gas is 2. So the way they react or the way they relate to each other is 1:3:2. We can simply say it this way. Let me say it in a way that we understand. It simply means that the way these gases they reacted is that 1 centimeter or cube of N2, that's 1 centimeter or 1 volume of N2 reacts with 3 volume or 3 centimeter cube. When it's centimeter cube, you know it's volume. So like 3 centimeter cube, you know this is 3 volumes also. This centimeter cube makes us know that the quantity is like the number is a volume, it's representing a volume. So this is 3 centimeter cube of H2 hydrogen gas to form 2 centimeter cube of ammonia. This is simply what Gay-Lussac's law is all about. So it's telling us that when there are gases in reaction, when gases are reacting towards each other, the way they react in simple whole number ratio. And that whole number ratio, the numbers in that whole number ratio is the stoichiometric coefficient in the balanced reaction, the balanced equation of the reaction. So this reaction must be balanced for you to be able to, for Gay-Lussac's law, for which you'll be able to apply Gay-Lussac's law of combining volume. Take note that this reaction must be balanced. Because when we balance the equation, if we don't balance the equation, we are not going to get the correct number, the stoichiometric coefficient, that the correct number. We are not going to get it. So you know that from this reaction, from Gay-Lussac's law of combining volume, 1 centimeter cube of nitrogen gas react with 3 centimeter cube of hydrogen gas to form 2 centimeter cube of ammonia. This is simply what Gay-Lussac's law of combining volume is all about. And using this knowledge, you can use it to determine a lot. We'll be looking at it. Like I said, we're solving like 10 different questions. There's one WAEC question that I modified, and then 9 UTME standard questions. So ensure you follow me. So having understand this, let's move to the next slide. Gay-Lussac's law of combining volume. What you can determine with Gay-Lussac's law of combining volume. What can you determine? I wrote these 5 things from the most of the things that you guys will be asked. Like 95 or 99% of times, you'll be asked your questions around these things. But wait, there's something I did not say here. Now, for this gas, there are conditions for the law to be applied. There are conditions that must be met. Number 1, it should be at constant temperature and pressure. It should be at constant temperature and pressure. It must remain constant. Also, it only relates to gaseous reactants and products. So once there is probably a liquid or there is a solid, we don't relate that solid. That solid is negligible. The volume is negligible. We only relate it to the gases in the reaction. So if, assuming this is a liquid, this does not stand anymore. It becomes 1 centimeter cube gives, and this is a gas, we give 1 centimeter cube gives 1 centimeter cube of nitrogen gas gives 2 centimeter cube of ammonia. So once there is a liquid or a solid, we cannot relate it. The volumes are negligible. So it only applies to gases in reaction, and if the gas is also a product. Also, for you to be able to apply it, you must ensure that you write the correct balanced equation. I've given 3 conditions now. First, that temperature and pressure must remain constant. Secondly, it only applies to gases in reaction, and also to the gas if it's a product, and also to the product if it's a gas, rather. You guys get. And number 3, you must write the balanced chemical equation. So let's move to the next slide. So what can you determine with Gay-Lussac's law of combining volume? Number 1, I wrote it here that you can determine the exact volume of gaseous reactant needed to react with another gaseous reactant. So exact volume of gaseous reactant needed to react with another gaseous reactant. Let's use an example to explain this. And that example is in question 1. So this says that what is the volume of oxygen required to burn or react? Burn means to react completely. To burn completely 45 centimeter cube of methane at STP. Let's quickly solve this. Remember, we are looking at number 1. I want to do it step by step. So we are looking at this number 1. What can you determine with Gay-Lussac's law of combining volume? The exact volume of gaseous reactant needed to react with another gaseous reactant. So you can be like the question here that we have here, we were given one gaseous reactant, the reactant of one of the volume of one of the reactants. So we can look for the volume of oxygen that is needed to react completely with this. So let's read the question again. What volume of oxygen required? What is the volume of oxygen required to burn completely 45 centimeter cube of methane at STP? So at STP. So um so the first thing to write, like I said, for you to be able to apply Gay-Lussac's law of combining volume is to write the balanced equation. Yeah, methane is a gas. Methane is a gas. If you remember, it's the first this thing in the alkane series. So methane, first compound in the alkane series, reacts with oxygen. They are both gases. Oxygen gas. Oxygen gas, remember, is O2. Oxygen gas is O2. To form what? It forms carbon dioxide or carbon dioxide plus water, plus water plus steam. All of them are gases. So now, this now is not balanced because here we have one atom of carbon, one atom of carbon, okay? We have four atoms of hydrogen, we have two atoms of hydrogen here, and we have four here, so it's not balanced. And then we have three atoms, O2 and one O. This is two atoms of oxygen, one atom of oxygen. So we have three atoms of oxygen, two atoms of oxygen. So it's not balanced. So let's balance this. This we have four atoms of hydrogen. So let's put two here. This becomes four. Two times two, four atoms of hydrogen. Okay. Now we have two atoms of oxygen, and we have two plus two. Two plus two. So we have four atoms of oxygen here. So to get the four here, we know that we should just add two here. So this becomes four atoms of oxygen, two plus two plus two. Two atoms of oxygen, two atoms of oxygen. So this equation is balanced. So we have four atoms of oxygen on the reactant side and four atoms of oxygen on the product side. So this equation is balanced. Always remember to write your balanced equation. Always remember, very, very important. As we continue, we will develop like a step-by-step method of solving questions on it. Just follow me. So from Gay-Lussac's law of combining volume, we know that the way they react is that they react, the ratio is 1:2, ratio 1:2. And where did I get this number from? The stoichiometric coefficient. This is one. There's invisible one here. Stoichiometric coefficient. Okay, so here we can say 1 centimeter cube reacts with 1 centimeter cube of methane reacts with 2 centimeter cube of oxygen to form 1 centimeter cube of carbon dioxide and 2 centimeter cube of steam or water. This water is like steam. So now what we are dealing with here is only the reactant. What is the volume of oxygen required to burn completely 45 centimeter cube of methane? So we are dealing here with only the reactant. They are asking us the volume of this of oxygen that we react completely with what? 45 centimeter cube of methane. So remember I said we can simply write this as 1 centimeter cube of methane react with what? 2 centimeter cube of oxygen gas. So from this equation that we have, from this knowledge we have, we can simply say, since we have 45 centimeter cube, we already know this from our balance equation. We already know it is a standard from our balance equation, and we got it from Gay-Lussac's law of combining volume. So we can say that since we have 45 centimeter cube, we can say 45 centimeter cube of CH4 we now react with how many centimeter cube of O2. So from here, you can just cross multiply and you get the exact amount of this that we react with this. I hope this is clear. So we already know this from Gay-Lussac's law of combining volume. It's just to put this 45 centimeter cube of methane. Ensure these two they are the same. Methane, 45 centimeter cube of methane. Now react with what centimeter cube of oxygen. So we cross multiply. So x times 1 is x equals 2 times 45 is 90. I'm cross multiply. I just want to quickly finish this. It's 90. So we have 90 centimeter cube of oxygen gas that will react completely with 45 centimeter cube. So if you divide, you say that the ratio is 1:2. If you divide this ratio, if you divide the ratio, you say that this ratio will give you 1:2. This ratio will give you 1:2. This is just how Gay-Lussac's law of combining volume is, how it works. It's very, very simple. Though there are still some other parts that you need to know, but this is one part where you can be asked remember what we are trying to get is the exact volume of gaseous reactant that will be needed, the exact volume that will be needed to react with another one. So here we got it that 90 centimeter cube of oxygen gas is the exact volume that is needed to react with 45 centimeter cube of methane. So that's the first one. So let's move to the next one. We have already solved this. So if you are given any question, on this, so you have solved this, you should know how to solve it now. So number 2 is we can use Gay-Lussac's law of combining volume to find the limiting reagent or the limiting reactant, which now is a gas. Remember, we are dealing with gases. So we can use it to find what? Limiting reagent or limiting reactant. What exactly is limiting reagent? Let me explain quickly. So limiting reagent is in chemistry, or let me just, is the reactant that gets used up first in a chemical reaction. In this case, we are talking about a gas. So just write it in your notes. I don't have too much space here. Let me just try to manage. Limiting reagent is what? Amount or reagent or reactant that gets reagent or reactant that gets used up first in a reaction. So once a limiting reagent finishes, the reaction stops even if the other one still remains. I'm going to explain. I'm going to use a simple analogy to explain. So once a limiting reagent finishes, limiting means is the one limiting the product. So for example, we have two things and one finishes first. Even if the other one is remaining, there's nothing that the one that finishes first will react with. There's nothing that the one that still remains will react with because the other one has finished. So the limiting reagent is the one that stops the reaction from continuing. Even if the other reactant remains, it is the reactant that determines the maximum theoretical yield. Take note that it is the one that determines the maximum theoretical yield. Let me use a simple analogy. Let me clean this. Let me use a simple analogy to demonstrate limiting reagent. So for example, you want to make toast bread. I hope this analogy works, but let me still use it. You want to make toast bread, and then there are two major ingredients that you need to make the toast bread, which is, let me say, bread and what? And egg. And to make one toast bread, you have to use 2 slices of bread or 2 slices of bread. Let me just do 2 bread plus 1 egg. 2 bread plus 1 egg gives what? 1 toast bread. So for example, this is the equation. I'm going to give you, this is just a simple analogy. There is still a way to get the limiting reagents during particularly for Gay-Lussac law of combining bond. I'll give you guys a trick, but I just want to use this to explain limiting reagents. So peradventure, to make a toast bread, your recipe is two bread plus two slices of bread, plus one egg to give one toast bread. Now, you now get to your kitchen, eh? You now see that you have 10 slices of bread. Let's say you have 10 slices of bread. 10 slices. You see that it's 10 slices of bread, and two eggs that you have. Okay? 10 slices of bread and two eggs that you have. So now you now start making your toast bread. You pick, you know that remember from here, we need one egg and two sliced bread to make one toast bread. So you pick two sliced bread here, and then one egg. You make one toast bread. You have made one toast bread. You now pick another two slices of bread and one egg. You now make another toast bread. So you have made two toast bread already. You have made two toast bread, but you cannot continue. Why? Because this egg has finished. You cannot continue because this egg has finished. Remember that you took two slices of bread first time, two slices of bread another time. That is four slices of bread. There are still six bread remaining, six slices of bread that is remaining, right? That means this egg is the limiting reagent or the limiting ingredient here, because this egg has finished and it is the one that determines what the toast bread, the maximum number of toast bread you can make here is with two, because you have two eggs alone, is two toast bread. Am I right? Yes, because you have two eggs and there's no egg anymore, even if you still have six slices of bread left, because you took four slices of bread. So these two eggs is what we call the limiting reagent. And the one that will now be in excess, there's one that is in excess, which is what? The slice of bread. The slice of bread is in excess. So this is what we call limiting reagent. I will tell you guys how to determine limiting reagent. So remember, the limiting reagent is the one that helps us to determine the maximum theoretical yield, because once it finishes, the reaction stops. Because even if we have six slices of bread, there's no egg that we are going to use to make that any toast bread from the bread anymore. There's no egg. So the egg is limiting the yield, is limiting the toast bread that we are going to get or we are going to form. The toast bread here represent the product. So two eggs. Yes. So you see that these two eggs helps us to get just two toast bread, because we have because the egg has finished. So remember, from here now we now have six slices of bread left. So this slice of bread is the one in excess. So once you just know that if you determine the limiting reagent and you get it as, okay, this is the limiting reagent, this bread is the one in excess, this one is the limiting reagent, the bread is in excess. So if one is the limiting reagent, one will be the excess reagent. So you have already determined the excess reagent already. So yeah, what is the excess reagent? The slice of bread. Simple. Now, there are times they can be asked how much of the excess reactant is remaining after reaction. What do you do? Okay, for example, they say you should determine how much of the excess reactant is remaining after the reaction. Remember, we say something is in excess. That means after reaction is still remaining. So from here, from this analogy I gave you, if you want to look for the excess bread that is remaining, how do you do it? It's 10 minus 4, that is 6. So the bread that you had before reacting minus the bread that we used in the reaction or in making our bread, in making our toast bread, will give us what? The remaining bread, that is the remaining bread, or the bread that is remaining. I hope this is clear. We are going to get it as we continue. Just follow me. So also, I think I've covered this. And I also added something. They can ask you how much of the excess reactant is remaining after reaction. So you just need to subtract the reaction before the reactant, the excess reactant, the volume of the excess reactant before reaction minus the volume of the excess reactant that is used during the reaction. So here we have 10. We have 10 slices of bread before we started making the toast bread, minus how many slices of bread did we use when we were making the toast bread? We used 4. So 10 minus 4 is 6. So we have 6 slices of bread remaining. So this is the excess, the remaining excess reactant. So is remaining by what? 6 slices. So 6 slices of bread is remaining. So the next one, we'll still solve examples, we'll still solve questions on it. The next one, the volume of gaseous product formed. 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 So yeah, let's use this analogy to determine it again. So once you can know your limiting reagent, you can also find the volume of excess product formed. How? We know that one egg, the volume of gaseous product, not excess product. One egg, we need, for one egg, we need 1 toast bread, right? And then, since we know the from the limiting reagent, 2 eggs, we give how many toast bread? Is the limiting reagent. We use the limiting reagent to also find that. We can use the limiting reagent. We can also use the other one, but I'm going to tell us as we continue. The other reagent that is in excess, but there's a way we have to do it. So 2 eggs will give how many toast bread? 2 eggs, cross multiply. 2 eggs will give 2 toast bread. So that is the product formed. And then total volume of gaseous, we can also use to determine total volume of gaseous mixture or residual gases at the end of the reaction. So when they say look for the total volume of gaseous mixture remaining, okay, let me just put it this way, using this analogy. When if they should say what is the ingredient, or no, how will I put it? I don't think I can use this analogy to explain. But you know that now in that container, let me say in that container that there is, that gases are reacting, reaction has occurred, so product has been formed. We have used up the limiting reagent and product has been formed, right? A product has been formed. So the product that is formed, assuming is a gas, so assuming is 40 centimeter cube that is formed, so we have that in the container. Another thing we now have in the container is the remaining excess reactant. The excess reactant remaining after reaction is done. So for example, after the reaction is done, the excess reactant remaining is 10 centimeter cube. So the total volume of gaseous mixture remaining, or the residual gases remaining at the end, will be 40 plus 10, which is 50 centimeter cube. I hope this is clear. We are going to use examples to explain. Let's just continue. So yeah, we already solved number 1, right? You already have gotten this. The remaining one will cover most of the questions we'll be looking at now. We cover the other part, this other part. This is a blank page. This other part, this limiting reagent, excess reactant, and all that. So let's look at question 2. Let's look at question 2. Solution. I don't know if this my green pen works. Let me just use my white pen. Solution. Now, this is a why question. I modified it, but it's almost like the same thing. So this says that Gay-Lussac law of combining volume. You know, it's the Gay-Lussac law of combining volume states that when gases react, they do so in simple number ratio to one another and to the volume of the product if gaseous, provided that the temperature and pressure remain constant. If you are writing WAEC, you can also add it. Conditions for this law to be applied: 1, balanced. There must be the equation must be balanced. 2, the temperature and pressure must remain constant. 3, it only deals with reaction between gases. That's an extra mark for you. the examiner will know that yes, you know what you are doing. So yes, the next question now says we have gotten this. The next question now says carbon 2 oxide reacted with oxygen to form carbon 4 oxide in a sealed tube. Write a balanced equation. So CO2, the CO, sorry, CO is a gas, react with oxygen gas. Oxygen gas is O2 to form what? CO2, carbon 4 oxide, right? They now said that we should write a balanced equation. Is this equation balanced? No, because we have one carbon atom. Yes, we have two, one plus two, two oxygen atom plus one. That's three oxygen atom in the reactant side and two oxygen atom in the product side. So this is not balanced. How do we balance it? So let's put two here. This becomes 4 and this becomes what? So we have two atoms of oxygen, 4, 2 times 2, 2 times 2, because this carries both of them. Both this belongs to both carbon and oxygen. So the total number of atoms of oxygen that we have is 2 times 2. That's 4 atoms. So we have 4 atoms here, 4 atoms here. So this is balanced. So this is a balanced chemical equation already. Balanced chemical equation. Right? Balanced chemical equation. So they now said that if 40 centimeter cube of carbon 2 oxide were mixed with 30 centimeter cube of oxygen, calculate the limiting reagent. Now, they said if the way they react, I think the first thing you write here, just 2 ratio 1, right? 2 ratio 1 here. You don't need to put any 1, but just know if there's nothing in front, the stoichiometric coefficient is 1 ratio 2. So now let's say calculate the limiting reagent. Remember I said I'm going to tell you guys how to calculate the limiting reagent. That one I gave was just an analogy. That is not a chemical reaction. Let me tell you guys how to find limiting reagent. It's very simple. When we talk about limiting reagent, note that we are talking about limiting reactants. Then we are talking about the reactants. Yeah, the reactants. That's limiting reagent here can either be carbon 2 oxide or oxygen. This is a product, not a reactant. This is reactant. So calculate the limiting reactant. What is the limiting reactant? This should be what is the limiting reactant? What is the limiting reactant? So how do you find reactant? So when you are asked to look for limiting reactant, what you do, take the volume of each reactant. Here we have 40 centimeter cube. Just you can write it somewhere. 40 centimeter cube, right? And we have 30 centimeter cube of oxygen. So take this reactant and then divide it by the stoichiometric coefficient. The stoichiometric coefficient here is 2. The stoichiometric coefficient here is 1. So divide the volume you were given by the stoichiometric coefficient. So this becomes 20 centimeter cube and this becomes 30 centimeter cube, right? The one that is smaller here is the limiting reactant. The one that is smaller here after you divide this is the one that is the limiting reactant, is the one that will finish first. So yeah, this is the smaller one. So carbon 2 oxide is the limiting reactant. Simple. This is the simple way to determine limiting reactant. So limiting reactant here is what? Carbon CO. CO is the limiting reactant. I hope this is clear. So just take the volume you were given, and then divide it by the stoichiometric coefficient. The smaller one is the limiting reactant. So we have determined the limiting reactant that way. So we know that CO is the limiting. Let me just clean this. CO is the limiting reactant. This place is small. I just hope it's able to help us. Just follow me. Follow me. Or let's use a blank space. Let's use a blank space for this. I think I have a blank space. Let's put solution. Let's use a blank space for this so that we can solve well. So remember what we have is we have CO reacting with O2. I want to solve that question now to give CO2. So we balance the equation 2 here, 2 here. So the way they react, the ratio is what? It's 2:1, ratio 2, right? So we have determined the limiting reagent. The limiting reagent is what? The limiting reagent is CO, which is CO. We have determined the limiting reagent. So limiting reagent, limiting reactant is equal to what? CO. So we know that already. So let's look at the next question they asked us to solve. They said that which reactant is in excess and by how much? So remember I told you that once this is the limiting reagent, this is the excess. So if this is the limiting reagent and the finishing force, this one automatically becomes the excess reactant. So the excess reactant is O2. Excess reactant is what? Is O2, oxygen gas. So the excess reactant here is O2. They now ask us that, let us go back to the question, no rush. They said, by how much is this reactant in excess? Remember, we have 30 centimeter cube. Now let me write the, we have CO rather to be 40 centimeter cube that we have, and O2 is 30 centimeter cube. That means this being the limiting reagent finished first, why this did not finish in the reaction or when they were reacting. So they now ask us by how much, or by how much is this one in excess? That means how much of this is remaining after the reaction. That's what they're asking us. How much of this is remaining after the reaction? I'm sorry about the noise. So how much of this is remaining? How much of the excess is remaining? Let me explain how to get it. So the first thing you need to look for now is to find the exact amount of this, volume of this that will react with this one. And I've told you guys how to get it. You have to first look for the exact amount of this that will react with this, and then you now subtract this from the exact amount of this that will react with this. That will be the remaining amount of this after the reaction has been completed. So now we have, remember from Gay-Lussac's law of combining volume, we have, I'm coming. So I already told you guys how to get. We need to first get the amount of this that will react with this, the exact amount of this, because not all of this reacted with it, because this is the limiting reagent. This is in excess, so not everything will react with this. So now I already told you guys how to look for it. This is the volumetric ratio. So we can say here that 2 centimeter cube of CO react with what's it called? It reacts with 1 centimeter cube, right, of oxygen gas to give 2 centimeter cube of CO2, right? So we are dealing with reactants here, remember. So we want to look for the exact amount of this that reacted with this. So we can now say 40 centimeter cube of CO will react with what? Centimeter cube of O2. This one has not reacted yet. This one, there's no, we are still doing, what we are looking for is, this one has not been formed yet. We just want to look for the amount of this. I just wrote this as per just talking about Gay-Lussac law of combining volume. This does not concern us. So yeah, what do you do here? You cross multiply. Want to look for the exact amount of this that will react with this. So we have 2 just ignore these volumes, these stuffs. So we have 2 times x is 2 times x equals 40 times 1, or 1 times 40, 1 times 40. So we have 2x equals 40. So 20 centimeter cube of oxygen gas. So we know that it's 20 centimeter cube of oxygen gas that will react with, that will react with 40 centimeter cube. I hope this is clear. This is the exact amount of oxygen gas that will react with this. Remember, it's in excess, so not everything will react. So we first look for, they now ask us for how much of the excess reactant is remaining. So we first look for the exact amount of this that will react with this. So 20 is the exact amount, 20 centimeter cube of oxygen gas is the one that is the exact amount that we react with this. So how many will remaining is 30 remaining oxygen, remaining O2 will be what? 30 centimeter cube minus 20 centimeter cube. So the remaining is 10 centimeter cube. I hope this is clear. The remaining is 10 centimeter cube. So this is the remaining. We have answered question 2. I'm still going to give like a very shorter method. I'm just trying to explain it. As we continue, I'll give you like a shorter method. So yeah, so we have looked for question 2. Let's go to the question. We have looked for the B part, I think. Let's go to the question. So this is what? O2 that is remaining, right? O2 that is the excess reactant, and is remaining by how much? 10 centimeter cube. They now ask us to calculate the volume of carbon dioxide produced. This carbon dioxide is the volume of the product. So what they're asking us to look for is the volume of the product. So how do we find that? Very simple. Sorry, very simple. Let me clean this. Permit me to clean this. We have found the volume of the product, and we have found the amount, the excess reactant, and the amount, how much of it is remaining. So volume of the product, let me just put amount remaining, O2 is 10, right? Which is 30 minus the 20 we got. So now, they now ask us to look for the volume of product formed. So because we are dealing with products, you just need to pick one out of these two. I prefer using the limiting reagent for this thing, for this particular part, where they ask us to look for the volume of the product that is formed. I love using the limiting reagent in order to avoid confusion. So I'm going to use this other one, the excess. I'm going to use it too, but for clarity's sake, let me first use this one, the limiting reagent. So how do we determine that? We say, since from the equation 2 centimeter cube of CO2 produce 2 centimeter cube of 2 centimeter cube of CO produce 2 centimeter cube of CO2, right? So 40 centimeter cube that we were given, remember we have 40 centimeter cube of CO will now produce how many centimeter cube of CO2? So the exact way we looked for the amount of oxygen that we react, the exact amount of oxygen that we react with the limiting reagent, that's the way we look for these two. So since from this volumetric ratio, we know that 2 centimeter cube produced 2 centimeter cube of CO2. So 40 centimeter cube will produce what? So just take note that once the stoichiometric coefficient of the product and the limiting reagent is the same, just know that it's the same that they are going to produce. It's still 40 that you produce. Once both of them are the same, now it's the same they are going to produce. Let's say this one is 1, it's still 40 they will produce. I hope this is clear. That's if they are the same. That's what I'm saying. They are the same. So here we have cross multiply. We have 2 times x equals 2 times 40, which is 80. 2x equals 80. We have 2 x equals what? 40 centimeter cube. So 40 centimeter cube of CO2 was formed. So 40 centimeter cube of CO2 was formed. Just follow me. As we solve more questions, you guys will understand. 40 centimeter cube of CO2 was formed. Simple. Then I asked us that what was the total volume of the gaseous mixture? Total volume of the gaseous mixture at the end of the reaction. Now, remember that the limiting reagent, there's nothing remaining because it has been used up. So that one is gone. But we still have oxygen left, 10 centimeter. And we then have a product form, which is 40 centimeter. So the total volume, both of them are gases. So the mixture that is remaining is 10 plus 40 is what? 50 centimeter cube. Simple. So we have solved this like this. So the volume remaining is this 40 plus the 10. This volume remaining is this 40 that was produced, and the 10 of the excess reactant, the amount of the excess reactant remaining after the reaction. So that's 40 plus 10. So it's 50 centimeter cube. Simple. So all your questions that they want to ever ask you is going to be around this, all this that we have mentioned: limiting reagents, the exact amount of a gaseous reactant needed to react with another gaseous reactant, the volume of the gaseous product form, the excess reagent, and how much is remaining. All the questions they will ask you, most of the questions will be around this. So let's solve more questions. Let's go to question 3. So solving more questions will help you understand and it will help you to be able to like solve things faster. So like I said, I'll be giving a shorter method. So ensure you follow me. So this question 3, solution. I want to give us step-by-step method now. So this question says 50 centimeter cube or 50 volume of hydrogen as packed with 20 centimeter cube of oxygen. That means this was reacted with this at 100 degrees Celsius and 1 atmosphere. The total volume of the residual gases. Just know that once you hear total volume of residual gases, most likely you are going to be adding the one that is remaining, the amount, the remaining of the reactant remaining, and the amount of the volume, the amount of the product remaining. So let's just follow me. So the first thing to do is to write balanced equation. So hydrogen gas here react with what? Oxygen gas to form water. Now the what was formed here is gas. Sometimes the reason gas was formed there, steam, they say it is at 100 degrees Celsius, so it's already steam. That's why this is what? Steam. There are some conditions that they will give. There are some conditions that we give that this will not be steam. This will be like a liquid. And what's it called? You have to take note of the condition, because at 100 degrees Celsius, water is already boiling, it's already becoming steam. So this is steam, gas. So this is gas, this is gas. You don't really need to put all these ones. I'm just putting in. So now the ratio, volumetric ratio is 1:2. Sorry, this is not balanced. This is not balanced. This is not balanced because we have 2 atoms of oxygen here and 1 atom of oxygen, 2 atoms of hydrogen, 2 atoms of hydrogen here. So let's balance. Let's balance. Oxygen, we have 2. So we have 2 atoms of oxygen. Oxygen is not balanced. Oxygen is already balanced. 2 atoms of oxygen, and here 2 atoms of oxygen. Here we now have 4 atoms of hydrogen, 2 times 2. So we just put 2 here. We now have 4 here. So we have 4 atoms of hydrogen here, 4 atoms of hydrogen. So this is already balanced. This is already balanced. All right. So let's continue. So we have written the what is the volumetric ratio now? 2:1 ratio 2. This is volumetric ratio. Volumetric ratio, right? 2:1:2. I'm supposed to come in. Hold on, guys. Please let me draw. I think we are going to need more space. So let's just draw this. Hey, God's in my hand. So we have the reaction is 2H2, right, plus O2 to give water. This first thing, write a balanced equation. Write balanced equation first. So the next thing, write the stoichiometric coefficient 2, or the volumetric ratio that represents the volumetric ratio 2 ratio 1 ratio 2. So this is the volumetric ratio. Volumetric ratio. This VR represents volumetric ratio. Now we are looking for the total volume of the residual gases. We have to find the limiting reagent. We have to find the limiting reagent. Yeah, we can say, we can just write this like 2 centimeter cube. Or the first thing, find the limiting reagent. After writing balance equation, find the limiting reagents. Limiting reagent is what? Hydrogen. Sorry. Limiting reagent is what? We cannot say is hydrogen straight up or oxygen. Either of them can be the limiting reagent. So how do we find the? Remember I told you, you take this thing that you were given, the volume you were given. Here we have 100. Hydrogen is 100 centimeter cube. Oxygen, hydrogen is 100. Oxygen is what? Oxygen gas is 20 centimeter cube. So divide it by the stoichiometric coefficient. Hydrogen gas here is 2. Oxygen gas here is 1. So this is 50 centimeter cube. This is 20 centimeter cube. So the smallest between them is the limiting reagent. So this one, oxygen gas, will be the limiting reagent. Oxygen gas will be the limiting reagent. Yeah. So we have determined the limiting reagent. Now we can just write this. Let me just I want to give a step-by-step method. Volume uh, before sparking, that means before they react, is 100 centimeter cube, and then 20 centimeter cube, right? This one has not sparked yet, so we leave this one as blank because this one has not been formed. They have not sparked yet. I want to try to give a proper format that you guys can follow. So 100, so this is volume before sparking, volumetric ratio, volume before sparking, right? So the next thing to look for is what? We already found the what? um we have already found, what's it called, the limiting reagent, which is 20 centimeter cube. That's oxygen. So using the limiting reagent, you have to first find the exact amount of hydrogen gas that will react with O2. How do we find this? We use the limiting reagent. We know that from this Gay-Lussac law of combining volume, 2 centimeter cube of hydrogen gas react with 1 centimeter cube of oxygen gas, right? So how many centimeter cube of hydrogen gas is needed to react with 20 centimeter cube? We are using this limiting reagent to find the amount of this that will be used up. Amount of this, because not everything will be used up because it's in excess. So we are looking for, we use the limiting reagent to find it, the one that we will use. So for example, it can be 20 centimeter of 5 centimeter or 50 centimeter of this that will be used eh, to react with this. So not everything will be used up. So we have to look for the one that is used up. So 20 centimeter cube of oxygen gas. So we cross multiply. X times 1 is X. 20 times 2 is 40. So 40 centimeter cube of what? Oxygen gas will be the one that is needed to react with 20 centimeter cube. Now, we can say volume after volume. I'm coming. I want to give it a name. Okay. So we have reacting, let me just put this as reacting volumes. So the volumes are reacted. You know that 20 centimeter cube was completely used, right? And then what else? 40 centimeter cube of oxygen, of hydrogen, sorry, this hydrogen, hydrogen gas was the one that was used, right? So 40 centimeter cube of hydrogen was the one that was used up. So from here, we can find the amount of hydrogen gas remaining, which is 100 minus 60. This one will be remaining volume, remaining volume, eh, will be what? Remaining volume. This is reacting volume and this is remaining volumes. So 100 minus 40 is 60 centimeter cube. 20 minus 20, this is used up, so this is 0. So this is no longer, this has been completely used up because it's the limiting reagent. Now, we need to look for the volume of gaseous product also formed, and we put it here. We can just put it here. The volume of gaseous product formed, you can use the limiting reagent to find it. So we can say 1 centimeter cube, this one, of what? Oxygen gas react with, forms, not react with, forms, because we were looking for the volume of the gaseous product form now. Forms or produces 2 centimeter cube of water. So 20 centimeter cube we produce how many? 20 centimeter cube of O2 we produce 100 centimeter cube of H2O. So you cross multiply, x times 1 is x, 20 times 2 is 40 centimeter cube. So this that was produced is 40 centimeter cube, right? So now the remaining volume after reaction will be 40 centimeter cube plus 60. I'm coming. I think there's been a mistake. Since not, hey God, it's not capturing my audio again. Okay, thought it was not capturing my audio again. Hold on. So the total volume of residual gases. Okay, we found. Oh, I was using 100. Oh my God. Sorry, I was using 100. Look at me. I am so sorry. It's not 100 though. It's 50. It's 50. That means we have to start this all over again. I am so sorry. I am so sorry. Ah, sorry, that was a mistake from me. How did I start with? Shit. It was 50. 50 is the 50. Sorry, let's quickly write this stoichiometric coefficient 1, 2. So we know that the volume, I gave a volume before sparking. Before sparking. That's the volume before sparking. That's the volume we're giving, 50 centimeter cube, and um ratio. Let's just put ratio 20 centimeter cube. So this one, the before sparking, no volume has been formed. So we just put dash here, right? Just put dash here. Sorry, that was a mistake that I made. You just put dash here because no volume has been formed. So we now look for, so we already know the, okay, let's solve the limiting reagent again. For hydrogen we have 50 divided by 2, 50 divided by 2, and for oxygen we have 20 divided by 1. So this is 25 and 20. So oxygen is still the limiting reagent. So from the limiting reagent we have to determine the exact amount of hydrogen gas that will react with oxygen gas. So how do we do it? We say since 2 centimeter cube of hydrogen gas react with 1 centimeter cube, of oxygen gas from Gay-Lussac's law. This one, eh? This one now from Gay-Lussac's law. This 2 centimeter react with 1 centimeter. So since we know that this is limiting reagents, we want to look for the reacting volumes. That means the volume of this that reacted with this one. So this will be how many volume of H2 will react with 20 centimeter cube of. Why am I using this 20 centimeter cube? Because it's the limiting reagent, is the one that determines the maximum theoretical yield. It also helps us determine the exact amount of this that will react with this, of the excess reactant that will react with it. So that's why we are using limiting reagent. So cross multiply, right? So we have x centimeter cube times 1 is still x centimeter cube. You can just put x times 1. Let's just put x times 1. X equals 20 times 2 is what? 40 centimeter cube of H2. So we know that the reacting volume of hydrogen, the amount of hydrogen that will react in the reaction is 40 centimeter cube. And the amount of oxygen that will react is 20 because it's the limiting reagent. It will be used up. Now, we can rule this now. We can now find, now I think we need to find this. Like I said, we need to find this one. Okay, let's just subtract this to find the amount of excess reactants remaining after reaction. So 10 centimeter cube. This one is what? 0. This one, there's nothing remaining. So this is the amount of the reactant remaining. This is not the total amount of the gases that is remaining. Remember, we asked to look for the total volume of the residual gases in the mixture. So this one too will be in the mixture, but also the volume of the product form will also be in the mixture. So we have to look for the volume of the product form. So how do we do it? We can use this limiting reagent. So one, we say that from the stoichiometric coefficient or from the volumetric ratio, we have 1 centimeter cube of oxygen gas produces 2 centimeter cube of hydrogen gas. So how many centimeter cube produces 2 centimeter cube of water, not hydrogen gas, water. So, or steam, is steam. So 20 centimeter cube of oxygen gas we form how many centimeter cube of what? Of steam. So we cross multiply here. X times 1 is x. 20 times 2 is 40. So we know that 40 centimeter cube was formed. So we can write 40 centimeter cube here. So 10 plus 40 is what? This is the total. This will be the total volume of residual gases in the mixture. 10 plus 40 will be the total volume of residual gases, because we have 10 centimeter cube of hydrogen remaining after reaction, and after reaction you know that there's product form, there's a product form, and there's an amount of product form which is 40. So 10 plus 40 is 50 centimeter cube. So this is the answer. Sorry for using 100, that was a silly mistake. Let's move to the next question. This says 10 centimeter cube. This is another question and it's quite tricky. Just follow me. Let me put solution first. Let's be fast with our. So 10 centimeter cube of CO, that's carbon dioxide, react with is mixed and sparked with 100 centimeter cube of air containing 21% of O2. Okay, so CO in the gases that are in air, it is O2 that it will react to. It is oxygen gas it will react to. So you should know is the reaction between C and CO and O2. So if all the volumes measured at STP is measured at STP, the volume of the resulting gases would be, so it's like in a container now. This is a container. There is sparked, the mixed CO plus air, and this air contains 21% of oxygen, and the reaction that will occur, what the CO will react with, the gas that the CO will react with, the gas that the CO will react with in this air is oxygen. So the reaction is between CO and oxygen. That's carbon dioxide and oxygen gas. So CO gives CO2. Just know that CO plus O2 gives CO2. You have to know equation well. So this is not a balanced equation. Yes. So let's balance it. We have 2 here, 2 here, we have 3 here. So let's just make this 4 and this becomes 4. So this is balanced. Ensure you write a balanced equation. So the volumetric ratio is going to be 2:1 ratio 2. Am I right? So now remember that I said okay. The next thing to write, let's just write volumes before sparking. Before sparking. Let's always write that. So we know that 10 centimeter cube, 10 centimeter cube of CO. And this one, they said 21% of O2 is in this air. So we say 25% of, we want to look for the volume of oxygen gas in this air. So that's 21%. 21% is 21 by 100 times 100. That's 21 centimeter cube. So this is 21 centimeter cube. So this, because it's before sparking, we don't need this one because the product has not been formed yet. So this 21 centimeter cube, I got it from this. So 21 centimeter, 21% of oxygen gas. This air contains 21% of oxygen gas. So and we have 100 centimeter cube of air. So we say 21% to find the amount of oxygen gas in this, the amount of oxygen gas in air. So we say 21% times 100. 21 over 100 times 100. So yes, the next thing is to look for what? The reacting volumes. The reacting volumes. Now, to find the reacting volumes, we first have to look for what? The limiting reagent. Limiting reagent, remember I said you should look for it. See, we bring the volumes of the reactant that we have. We have 10 centimeter cube of CO and 21 centimeter cube of oxygen gas. So you divide it by the stoichiometric coefficient, divide by 2, divide by 1. So this is 5 centimeter, this is 21. So the limiting reagent here is CO because it's smaller. So the limiting reagent is CO. So how do we now find? We now need to look for the reacting volumes. We already know the reacting volume of CO is 10 because it's the limiting reagent. That's the reacting volume. So we now need to look for the amount of oxygen gas that we react with this. The exact amount of oxygen gas, because this we will not use, because this is in essence, we are not going to be using this one finish, like it's not going to finish. So we need to look for the one that we react with it. That's what we call the reacting volume, the one that we react with it. So we say from here, from this stoichiometric coefficient, you can say 2 centimeter cube of CO react with what? 1 centimeter cube of oxygen gas. 2, this 2, 1, yeah, 1. So 2 react to 1, and then the limiting reagent will be used to determine the exact amount of this one that will react with it. So 10 centimeter cube of CO will react with how many centimeter cube of O2? So cross multiply. 2 times x, 2x. 10 times 1 or 1 times 10 is 10. So 2. So x equals 5 centimeter cube. So 5 centimeter cube of oxygen gas will react with what? 10 centimeter cube of CO. So we know that reacting volume here is 10 centimeter cube and 5 centimeter cube, right? The product, we are still going to find the volume of the product form. So the volume after sparking, you know this one is 0 because it has been used up. This one is going to be what? 21 minus 5 is 16 centimeter cube. So oxygen is remaining 16 centimeter cube in this container. 5 centimeter it has reacted. It has reacted. So we need to also look for the volume of the gaseous product formed. Remember, I told you that for clarity's sake, just use limiting reagent to find it. So you use the limiting reagent to find the exact amount of this that will react with it and the volume of the product formed. So we can say here that 2 centimeter cube from this volumetric ratio, 2 centimeter cube of CO react with 2 centimeter cube, not react, forms because we are looking at the product, forms 2 centimeter cube of CO2. 2 centimeter cube forms 2 centimeter cube. Let me use my green pen. 2 centimeter cube forms 2 centimeter cube, right? So 10 centimeter cube, the limiting reagent, 10 centimeter cube of CO will form how many centimeter cube of CO2? So cross multiply. I told you, remember I said something that once both of them have the same stoichiometric coefficient, just know that it's the same volume that will be produced. Once the limiting reagent and the volume, the product formed, once the limiting reagent, the stoichiometric coefficient of the limiting reagent and the product form is the same, this thing they are going to produce. So if you do it, 2 times 2 is 2, 2 times x, sorry, is 2x. 2 times 10 is 20. So divide both side by 2. We have 10 centimeter cube. So 10 centimeter cube of CO2 was formed. So the volumes after sparking, we have 10 centimeter cube. 10 centimeter cube. So 16 plus 10. So 16 plus 10 is 26 centimeter cube. Now, 26 centimeter cube is not the total volume of resulting gases because air contains gases. So we have 100 centimeter cube of air before. We just look for 21% of it, which was the oxygen, amount of oxygen that was in the air. So remember that we got 21 centimeter cube as the amount of oxygen that is in the air. So the remaining amount of gases in the of this air that is in the container will be is 100 minus 21, which will give us 79 centimeter cube. So there are some other gases that have a total volume of 79. So plus this 26 that we have gotten, 79 plus 26 gives us 105 centimeter cube of resulting gases. You must be very careful and look for the exact one they ask you to look for. Yeah. Now, let me just do a brief recap. Let me quickly do it. We are still in question 4. Okay. Let me just quickly do a brief recap. So, we already look for the amount of oxygen remaining, oxygen gas remaining, and then we look for the volume of the product form, the volume of oxygen gas remaining, the volume of the product form. They are the ones that will remain. Those ones too will remain after reaction. They'll be there after reaction. And then because we have 100 centimeter cube of air, we just got 21 centimeter cube of oxygen from that air, and air contains gases. That means in that container, we still have 79 centimeter cube of the gases, other gases remaining. Those gases are the gas that make up air plus oxygen too. So they are 79. So it is 79. We have 79 volumes of the remaining gases that represent air there. So we add it to this as 105. So the answer is 105 centimeter cube of resulting gas. So this is the answer. Let's move to the next question. This question says, I hope I don't take time here. Let's see if we can quickly solve. What 100 centimeter cube of oxygen is made to react with 50 centimeter cube of hydrogen? Let's just write solution. Let's draw. So you know that it's between hydrogen and oxygen, hydrogen gas, and oxygen. And the whole reaction was then passed through anhydrous carbon, calcium chloride. This is very, very important. Know that calcium chloride absorbs water, can absorb steam, can absorb this thing, water. So you know that what is the volume of gas left? We don't need the product anymore because this will absorb the product, water. So be careful of the conditions they are giving because they said they pass through calcium chloride. So yeah, I remember I said always find the balanced equation. The volume of the gas left will be the one of the excess reactant because from here H2O we don't need it anymore because this will absorb it. Anhydrous calcium chloride absorbs water. It absorbs steam. So you guys should take note of that. So we have the balanced equation. We have 2 here, 2 here. So the volumetric ratio 2:1, ratio 2. Volume before sparking. Volume before sparking is what? 100. We have, oh no, we have 50 centimeter cube of hydrogen gas and then 100 centimeter cube of oxygen gas. So this one has not been formed yet. We don't even need this one. In fact, we don't need this one again because it will. You don't need to look for this one again because this will absorb it. So for time's sake, we are not going to solve it. So the volume of gas left will be the volume of the excess reactant left after reacting. So now you know that for we to look for the volume of excess reactant left after reacting, we have to find the exact amount of the excess reactant that will react with the limiting reagent. So let's find the limiting reagent next. So limiting reagent, um, the limiting reagent. Remember how I said you should find limiting reagent. We have hydrogen gas, oxygen gas. We have 50, we have 100, 50 centimeter cube, 100 centimeter cube, right? So divided by the stoichiometric coefficient. So we have 25 centimeter cube of hydrogen gas, 100 centimeter cube of oxygen gas. So the smaller one is the limiting reagent. That means the limiting reagent here is hydrogen gas. So hydrogen gas will finish first. So we now need to look for volume, reacting volumes. Let's look for reacting volumes. So we know that since this one will finish first, the reacting volume is 50 centimeter cube. But we have to look for the reacting volume of this 100 of this oxygen gas that we react with this, because not everything we react with hydrogen. Not all the oxygen we react with the hydrogen because oxygen gas is in excess. So how do we do it? From this volumetric ratio, we can write it 2 centimeter cube of hydrogen gas react with 1 centimeter cube of oxygen gas, right? So using this, the limiting reagent, 50 centimeter cube of hydrogen gas will now react with how many centimeter cube of oxygen gas? So 2, we cross multiply, 2 times x is 2x, 50 times 1 is 50. So divide both side by 2, x equals what? 25 centimeter cube. So 25 centimeter cube 25 centimeter cube of oxygen gas will react completely with 50 centimeter cube. So this is the reacting volume. 25 centimeter cube of oxygen gas is the reacting volume. So we subtract it to find the remaining amount of the excess reactant remaining. The excess reactant remaining, or the remaining amount of the reactant, of the excess reactant. So this is 0, and this will be 100 minus 25 is 75 centimeter cube. So 75, after reacting, 75 centimeter cube of oxygen gas will be remaining because it's the one in excess. This one cannot remain because it is the limiting reagent, it will be used up. So the answer is 75 centimeter cube. The reason we did not look for this is because calcium chloride will absorb it, so we don't need it. So the volume of gas left after everything, because they pass it through calcium chloride, anhydrous calcium chloride, and it will what? It will um it will um absorb it. So we don't need this. So always check the conditions. So the answer is 75 centimeter cube. Let's quickly go to question 6. Question 6. Okay, solution. The same condition, calcium chloride. So once you see calcium chloride is formed and it's passed to calcium chloride, don't just look at the product form, because especially if it is between hydrogen gas and oxygen gas, because steam or water will be formed and calcium chloride actually absorb steam or water. So 20 centimeter cube of hydrogen gas are packed with 20 centimeter cube of oxygen gas in an endemotor. Idiometer. 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 It is used to measure volume changes in gas mixtures during reaction. So this was idiometer. So it's not really necessary, but then idiometer. The resulting mixture is cooled to 25 degrees and passed through what? And passed over calcium chloride. So the volume of the residual gas is, you know that the volume of the residual gas will be the volume of the excess reactant remaining after reaction, because we really don't need this anymore. Because first, steam was formed 100 degrees Celsius, but then it was cooled, then it became water, became liquid, and then it was passed to calcium chloride. So we really don't need the products anymore, because we don't need it. So the volume of the residual gas remaining will be that of the excess reactant that is remaining after reaction. So the first thing, remember, always write a balanced equation. By now you should know the balanced equation of between hydrogen gas and oxygen gas to form water or steam. 2, so 2 here, 2 stoichiometric coefficient, volumetric coefficient, 2:1, ratio what? 2. 2:1, ratio 2. 2:1, ratio 2. 2:1, ratio 2. So we need to, I usually write volume before sparking, right? So the volume before sparking is 20 centimeter cube of hydrogen and 20 centimeter cube oxygen. This is not needed. Volume before sparking, normally this is not needed. So now the next thing is to look for the limiting reagent. So the limiting reagent here, remember how I told you guys to look for it? H2O2, we have 20 centimeter, 20 centimeter, divided by the stoichiometric coefficient 2 and 1. So this gives us 10 centimeter cube and 1 and 20 centimeter cube. So this is the limiting reagent. This is the limiting reagent, 10 centimeter cube, because it's the smaller one. So reacting volume, you know the reacting volume of hydrogen gas will be 10, will be, sorry, reacting volume will be 20 centimeter cube, because it's the limiting reagent. This 10 centimeter cube does not matter. We just use this to look for limiting reagent. That means this just tells us, getting this just tells us the one that is the limiting reagent. So we know that hydrogen gas is the limiting reagent. That means all volumes of hydrogen gas, all volume of hydrogen gas will be used up. So the reacting volume of hydrogen gas is 20 centimeter cube. 20 centimeter cube. We don't know the reacting volume of oxygen gas because it's the one in excess. That means after the reaction, there will be an amount of oxygen gas that will be remaining because it's the one in excess. So how do we look for it? I already told you guys how, you guys should know it by now. So we take the stoichiometric coefficient, or the the volumetric ratio. We can write it as 2 centimeter cube of H2 hydrogen gas react with 1 centimeter cube of oxygen gas, or react with 1 centimeter cube of oxygen gas. So since this is the limiting reagent, we use it to look for the exact amount of oxygen gas that will react with it. So we say 20 centimeter cube of H2 will now react with how many centimeter cube of O2? Cross multiply. So 2 times x is 2x, 20 times 1 is 20. 20 times 1 is 20. Divide both side by 2. X is what? 10 centimeter cube. So we have 10 centimeter cube of oxygen that will react with 20 centimeter cube. So this 10 centimeter cube is the one that will react. The entire 20 centimeter cube will not react. So we now look for volume after reaction. Volume remaining after reaction. This one will not be remaining. This volume after reaction is VAR, is volume after reaction. So the volume remaining will be 20 minus 10, it's 10 centimeter cube of oxygen. This, we don't need this again because first, steam was formed and then the mixture was cooled. So it became water. It reduced, like from 100 degrees Celsius, the temperature was cooled. So it became liquid and it was now passed through what? It was passed through um, calcium chloride, which absorb water. So this is not needed. So the volume of residual gas remaining is going to be 10 centimeter cube. So let's move to the next one. Okay. So this says, let me write quickly a solution. The minimum volume of oxygen required for the complete combustion of a mixture of 10 centimeter cube of CO and 15 centimeter cube of H2, the minimum volume of oxygen that we the minimum volume of oxygen required for the complete combustion of 10 centimeter cube of OK and 15 centimeter cube of H2O. This is very simple. So we need, okay, let's say in the container we have CO, we have H2, and we have O2. 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 Oxygen, this is oxygen gas, not just oxygen. O2. So when they reacted, let's see, CO react with oxygen gas to give CO2, right? CO2. And also H2 H2 react with O2 to form what? H2O. This we write the okay, no, sorry. This is O2. So oxygen can react with CO, oxygen can react with H2. So let's just find the minimum amount of oxygen that is required for complete combustion of both of them. So we assume that oxygen reacts with both of them. So from here now, stoichiometric coefficient 1 ratio 2. We are dealing with the reactant alone, so we don't need this. We don't need this. We are dealing with the reactant alone, so we don't need this. 2 ratio 1. So from here, remember they said we have 10 centimeter cube. We don't need limiting reagent here because we are looking for the oxygen that will completely react with this and completely react with this. So 10 centimeter cube of CO will, remember how I said you should look for, when you want to look for the amount of oxygen that will completely react, or the amount of a gaseous reactant that will completely react with another one, is simple. So we just say 1 centimeter cube of CO react with 2 centimeter cube of O2, then 10 centimeter cube of CO will now react with what? Will now react with what? So we have, sorry, this is not, hold on, this is not correct. This is not correct. Sorry, this is not correct. So balance the equation. 2 here, 2 here. So this becomes 2 ratio 1. I'm so sorry. That was a mistake. Balance the equation. Always balance the equation. So we can write it that 2 centimeter cube of oxygen gas, of, I said oxygen, CO, react with 1 centimeter cube of O2, right? So since we have 10 centimeter cube of CO, so we say 10 centimeter cube of CO will now react with how many? So this times, so we have how many centimeter cube of O2? So we have 2 times x, 2x equals 10 times 1, 10 centimeter cube. So we have 2, 2, x equals 5 centimeter cube of oxygen. Wait, let's solve for the second one and let's see if it will give us 5 too. So 2 centimeter cube of hydrogen gas will react with 1 centimeter cube of oxygen gas, right? And we have 15 centimeter cube. Okay, 15 centimeter cube of, okay, 15 centimeter cube of, so 15 centimeter cube of um hydrogen gas will now react with what? So X will now react. Remember, I don't just want to put it. This H2, 15 centimeter cube H2, 1 centimeter cube H2, O2. How many centimeter cube? 15 centimeter cube of H2 will now give what? How many centimeter cube of O2? So we are looking for the one that will react with this one. So X, 2 times X is 2x equals 15 times 1 is 15. 2 divided both side by 2. So 7.5 centimeter cube of O2 of oxygen gas will react with 15 centimeter cube of hydrogen gas. What do we do here? We now add both of them. Remember, we are looking for the minimum amount, the minimum volume of oxygen required for the complete combustion. That means when we put, let's say we put 5 centimeter cube of oxygen, that 5 centimeter cube will only be able to react with CO, right? But then when we now put 12.5, 7.5 plus 5 is 12.5 centimeter cube. When we put 12.5, 5 out of it, 5 volume of oxygen gas will first react with this CO, and then the remaining 7.5 will now completely react with what? The hydrogen gas. So that's what they are that's why we are looking for the amount, the minimum amount of oxygen gas that will react with both CO and H2. So that's why I gave two different equations. So the answer is what? 12.5. We look for the amount of oxygen that will react with CO and the amount of oxygen gas that will react with H2, and we added both of them. So simple. Let's go to another question. We have, after this, we have 2 more questions. Solution. What volume of oxygen will remain after reacting with 8 centimeter cube of hydrogen gas with 20 centimeter cube of oxygen gas? Okay, you know this is very simple. You guys should know this by now. So we are looking for the volume of oxygen remaining. So write a balance equation. H2 react with O2 to give H2O. 2, 2. So 2 ratio 1. Ratio what? 2. We don't need this one because we are looking for only the volume of oxygen that react. So the next thing to look for is what? Limiting reagent. So for H2, we have 20 divided by 2. It gives us 10 centimeter. For O2, we have, no, for H2 is 8 centimeter. Sorry, 8 centimeter. 8 hydrogen gas, 4 centimeter cube. O2 is 20 divided by 1. This gives us 20 centimeter cube. So hydrogen gas is the limiting reagent. So the volume before sparking, let's just write volume before sparking or reaction. Volume before reaction is 8. We are giving 8 centimeter cube of hydrogen gas, and then we have 20 centimeter cube. So these are the volume before sparking. So the reacting volume, since hydrogen gas is the limiting reagent, we know that it will be completely used up. So the reacting volume becomes 8 centimeter cube. It will be completely used up. So that is the amount, all the amount of hydrogen gas will react. But we know that oxygen gas is the reactant in excess. So it's not going to react. Not all the oxygen gas will react. Not all the volumes of oxygen gas will react with the hydrogen gas. So we have to look for it. So remember what I told you guys. We write this as 2 centimeter cube of hydrogen gas. This reacts with 1 centimeter cube of oxygen gas. So 8 centimeter cube, we use the limiting reagent to find the exact amount of excess reactant that reacts with it. H2 will now give us how many, will now react with how many centimeter cube of O2. So 2 times x is 2x, 8 times 1 is 8. So x equals to 4 centimeter cube of O2. So 4 centimeter cube of O2 will react. This is the amount of oxygen gas that will react with this. So we know that volume after sparking, this is 0 because everything will be used up. This one, there's nothing left for hydrogen gas, but there's still something left because this is in excess. How do you calculate this? We subtract 20 minus 4 is what? 16 centimeter cube. Simple. Simple. So question 9 quickly. Okay. Solution. Let's quickly write solution. So it says 25 centimeter cube of hydrogen was packed with 12 centimeter cube of oxygen gas. At just now they are gases. So when they say 25 centimeter cube hydrogen gas and oxygen gas at 110 degrees Celsius and 760 millimeter mercury to produce steam, what percentage of the total volume of gases left after reaction is hydrogen? The product is important because steam was produced and there was no other condition. Steam was still there as a gas. So what do we look for? We look for the total volume of gas left after reaction first. So we know that the total volume of gas left after reaction will be the steam, the volume of steam, and the volume of the excess reactant remaining after reaction. So the first thing to write is balanced equation H2 plus O2 to give H2O, right? So this is 2. By now you should know this. So write the stoichiometric coefficient, which is 2 ratio. The volumetric ratio is 2 ratio 2 ratio 2. 2 ratio 1 ratio 2. Volume before sparking. We have how many? We have 35 centimeter cube of oxygen, right? Sparked with 12 centimeter cube of hydrogen. This does not have a volume yet because no product has been formed before sparking. So now, the next thing to look for is the limiting reagent. So limiting reagent, we have 25 centimeter cube of hydrogen gas and what? 12 centimeter cube of oxygen gas. So divided by its stoichiometric coefficient. So here, I think this is going to be 17.5 centimeter cube, 12 centimeter cube. So the smaller one, oxygen, is the limiting reagent. So oxygen will be the one that will be used up. So reacting volume, we know that the reacting volume will be 12 centimeter cube for oxygen because it was the one that was used up. So we now look for the amount of hydrogen gas that we react with 12 centimeter cube of oxygen because hydrogen gas will not be used up because it's in excess. So how do we do it? Remember, from the volumetric ratio, we can say 2 centimeter cube of hydrogen gas react with 1 centimeter cube of oxygen gas. So how many centimeter cube, because we are looking for this, how many centimeter cube of hydrogen gas will now react with 8 centimeter cube of oxygen gas? We cross multiply. X times 1 is x. 2 times 8 is 16. So 16 centimeter cube of hydrogen gas, this x is 16 centimeter cube of hydrogen gas will react with 8 centimeter cube. So the reacting volume of hydrogen gas is 16 centimeter cube. So here we subtract. So 35 minus 16 should give us what? That should be 19 centimeter cube. So this will give us 0. Now, we need to also look for the volume of the gaseous product formed here because if gas was formed, it is needed here. So how do we do it? We also use the limiting reagent. We say that since oxygen is the limiting reagent, we say 1 centimeter cube of oxygen produces 1 centimeter cube of oxygen gas produces 2 centimeter cube of water. 1 centimeter cube of oxygen gas produces 2 centimeter cube of water. 1 centimeter cube of oxygen gas produces 2 centimeter cube of water, right? And then 12 centimeter cube of oxygen, we use the limiting reagent, this 12 centimeter, the amount of the limiting reagent we have. So 12 centimeter cube of O2 will now produce how many centimeter cube of H2O? Cross multiply. So x times 1 is x, 2 times 12 is 24 centimeter cube. So 24 centimeter cube of H2O of steam was produced. So this is 24 centimeter cube. So this is 24 centimeter cube. So the amount of water produced is 20, or steam produced is 24 centimeter cube. So the total volume of of gases remaining after reaction is going to be this plus this. So 19 plus 24, that this is 3, this is 3, this is 1, 1 plus this, yes, this is 3, 1, that's 43. So 43 centimeter cube was remaining. But now if you look at the the question, it says what percentage of the volume of gas left after reaction is hydrogen. Remember, 19 centimeter cube of hydrogen was remaining. So we are going to say 19 centimeter cube divided by the total volume remaining, the total volume of the residual gases remaining, times 100. So this is the percentage of hydrogen gas that is remaining out of the total volume of gas remaining. Always ensure that these are different. That's why I gave different scenarios. So 19 divided by 43 times, I think I made a mistake. I made another mistake. Sorry. So yeah, we need to go back. I made mistake. I was using 8 centimeter cube and it was 12 centimeter cube that was given. Oh my god. So sorry for the mistake. That's a silly mistake because I'm trying to rush because it's almost 2 hours now. So yeah, we have to clean this because we don't know it. This is not correct yet. This is not correct. This is not correct. So we need to look for the volume of hydrogen gas that will react with 12 out of this 35. So we say 2 centimeter cube of hydrogen gas react with 1 centimeter cube of oxygen gas. So how many centimeter cube of hydrogen gas will react with 12 centimeter cube? Is 12, not 8, of oxygen gas. So x times 1 is x, 12 times 2 is 24. So we have 24 centimeter cube of hydrogen gas that will react with this. So the reacting volume that reacts with 12 centimeter cube. So the reacting volume is 24 centimeter cube. So 24 centimeter cube will react with 12. So this is the reacting volume. So this gives us what? 11, right? It gives us 11 and this is 0 because this will be used up. Now, we need to also look for the residual, I said residual, the volume of steam that is formed. That's the volume of the product that is formed. How do we find it? I told you guys to use the limiting reagent. We can also use other things. I did not mention it, but use the limiting reagent for easy sake, for things to be easier. So we say we can equate it here from the volumetric ratio that 1 centimeter cube of O2 react with 2 centimeter produces, not reacts now, produces 2 centimeter cube of steam. Then this 12 centimeter cube of O2 will now produce how many centimeter cube of steam? So cross multiply x times 1, we have x, 12 times 2 is 24 centimeter cube of steam will be produced. So this is what? 24 centimeter cube. So this is 24 centimeter cube. So the volume after reacting, the volume that we have after reacting the container, we have 11 centimeter cube of hydrogen gas, 24 centimeter cube of steam. So the total volume of residual gases remaining is 35 centimeter cube. So they now ask us to look for, that's 24 plus 11. They now ask us to look for the volume, what percentage of the total volume gas of the gas left after reaction is hydrogen. So remember 11 is remaining. 11 centimeter cube of hydrogen is remaining. So we are looking for the percentage. They are saying what percentage of the total volume 35 is 11 centimeter cube. This is what they're asking. What percentage, what X percentage of the total volume 35, this is the total volume of the residual gas remaining 35, left after the reaction is equal to the one for what is equal to hydrogen. What volume of what total, what percentage of the total volume of gas left after reaction, total volume of gas is hydrogen, remember this is hydrogen, this is the total volume of gas. This is like word problem, I turned to a mathematical equation. So what do we do here? Remember, x is what? X percent is x over 100 times 35, right, equals 11, right? So here x times 35, this you can put it over 1. X times 35 is what? Is 30. X times 35 is, let's just put it 35x over 100 equals 11. So this one over 1, we cross multiply. What should we do? Where should we do? Let's just clean. We cross multiply. So we have, okay, let me write it here. 35x equals 11 over 1 over 100. So cross multiply. 35x times 35 is 35x. 100 times 1 is 1100, 1100. So 1100 divided by 35, that's 31. We have 31.4. So x is 31.4%, which is also 31%. So this is the correct answer. Because of time, let's go to the next question because time is almost fast spent. So yeah, this last question from the equation. I hope my battery does not go down because my laptop is saying 9% now. So from the equation above, the volume of oxygen required to burn 50 centimeter cube of propane. This is very simple, very simple. Volume of, we are dealing with the reactant here, so we have C3H8 5O2, right? We don't react with 5O2. We don't need this one again because we are looking for oxygen, the one oxygen that will react with what? Propane. So we know that from here, 1:5, right? We can say 1 centimeter cube of propane, C3H8, react with what? 5 centimeter cube of oxygen gas. This one is very simple. So they said we are given 50 centimeter cube of propane, so we are looking for what amount of this will be required to react with this. So 50 centimeter cube of propane will react with how many centimeter cube of oxygen? So x times 1 is x, 5 times 2 is 250 centimeter cube. This one is simple, of oxygen. So this is the amount of oxygen that we completely burn or completely react with propane. 50 centimeter cube of propane, 250. Correct. That's it. So this is the assignment that you guys should try to solve. These are also UTME questions. You see, it's UTME 2002, UTME 2012, UTME 2013. So if you enjoyed this video, ensure you like, you subscribe, and you share it. Also, you subscribe for more tutorial videos. Let me give you coming. Sorry. So that's our assignment. Ensure you do the assignment and drop the answer in the comment section. And then you like, you subscribe, and you share for more tutorial videos.